All right, so our second part of 2.7, our second video, we're talking about composition of functions. Now, you've seen composition of functions before, okay? Today we're talking about composition. So our notation, F circle, remember in the last video I told you that if it's closed, it means multiplications. Well, if it's open, the circle is open, it means something different. That's what we're getting in today. F of g of x. Okay, that's how that is written. Okay, think about this as kind of some substitution. I'm substituting g of x in for x in f of x. I'm taking g of x and plugging it in for x in f of x. Right? Think of it as substitution. Okay? Or composing functions. Read f of g of x. Alright, so if you remember in the first video we talked about these circles, okay, where I have x and this is my domain. Okay, and I apply a function to it. Let's say that function is k. So then my result would be k of x, which is my range or my output. Alright? Well, now, similar beginning, still starting with x. Okay? Applying something to it, applying our function k to it, which our result is k of x, which is our range. Alright? But now we're going to take k of x and apply another function, we'll call that j, to k, so that we have, or now we have, j of k of x, which is a composition of functions. So this would be our range of j. Alright, so really what we're doing is, this is technically here, our k of x is technically our range of j. This would, excuse me, not range of j, this is our domain of our j function. Okay, so really if you think about the composition of functions, well, if I'm inputting x, I could jump all the way here to j of k of x. Alright, so that's kind of the circle example of a composition of functions. So let's see what that looks like with some mathy stuff. Wow. Wow. Okay. So here f of x is x squared. Well, this one is a little bit of a review. I'm trying to find f of negative 3. That means wherever I see x and f of x, I replace it with negative 3. Order of operations, negative 3 squared is 9. Okay. Now we have f of g of negative 3. Composition of functions, just like from before, we're looking from the inside out. Okay, so I want to first deal with g of negative 3. Well, g of negative 3, plug negative 3 in here. Oops. Oh, how about that? G of negative 3 gives me 3 times negative 3 minus 1. 3 times negative 3 is negative 9, minus 1 gives me negative 10. So now, instead of g of negative 3, I just found out that g of negative 3 was negative 10. I want to find f of negative 10. Okay. F of negative 10 should give me negative 10 squared, which is 100. So my answer is 100. This is a two-step process. I find g of negative 3, which I got negative 10, and then I take that negative 10 and substitute it into f for x, and find f of negative 10, which gives me 100. Okay? We're working from the inside out on that. Alright, next little example of a composition of functions. Okay, so if f of x is x squared and g of x is the square root of 1 minus x, okay, f of g of x would then be the square root of 1 minus x quantity squared. What I'm doing is I'm taking my function g and plugging it in for x. You simplify that, squaring a square root gives us 1 minus x. Okay? So using the same composition or composite function, g of f of x, that is, replace all x values of g with the function f. Okay? So we're going to go g of f of x. Alright? So f of x is x squared. That means wherever I see x In G, I write x squared. So my composition of functions will be 1 minus x squared. Like that. Okay. Now we want to think about, whoops. Now we want, oh boy. Okay, now we want the domain. We want the domain of our composite functions. Okay, so if we think about the domain of our original functions here, x squared is all real numbers. 1 minus, the square root of 1 minus x will give me, remember, underneath the square root. Thinking about numbers underneath the square root, they have to be greater than, they cannot be negative. So that would have to be greater than or equal to 0. Or x, 1 is greater than or equal to x, or x is less than or equal to 1. That would be G. F we said was all reals. Okay, so now let's think about, this function here, g of f of x. All right, in g of f of x, we have to decide what our domain is there. Well, still, we cannot take the square root of a negative number. So underneath our square root, 1 minus x squared must be greater than or equal to 0. All right, so it's kind of tough to think about taking the square root. Well, I could factor this thing about as a polynomial. 1 minus x, 1 plus x must be greater than or equal to 0. Okay, then zero product property. What the heck? I can set each factor equal to 0. 1 minus x is greater than or equal to 0. 1 plus x is greater than or equal to 0. Add the x. 1 is greater than or equal to x, or x is less than or equal to 1. Subtract x. 1 is greater than or equal to negative x. Remember, if you divide by a negative, you flip the sign. So negative 1 is less than or equal to x, or x is greater than or equal to negative 1. Okay? So here are our two restrictions on our domain for g of f of x. Well, if we think about our other functions, okay, f of x just in general is all real numbers. Well, that's not going to fly here. Okay? G of x, x is less than or equal to 1. Well, that was part of it. That was part of our domain of our composite function. So I'll write that. X is less than or equal to 1. The second restriction, x must be greater than or equal to negative 1. Well, I can include that like that. Okay? So our domain is that x must be between negative 1 and 1. All right? And if talking about all this kind of confused you, think about your restrictions on this function here as well. All right, when you're thinking about the domain. All right, so just like in a lot of math, the cool part about it is trying to apply it to the real world. All right, math, IRL, okay, in real life. Here we go. So the graph at the left shows the swimmer's speed as a function of time. The graph at the right shows the swimmer's oxygen as a function of s, or speed. Okay, time is measured in seconds, speed in meters per second, oxygen consumption in liters per minute. Okay, so in composition of functions, we can do a lot of real world problems. All right, but we're going to start simple here. What is the speed after 20 seconds of swimming? So what's the swimmer's speed? So here's time, here's 20 seconds, boom, it's 1.5. Okay, similarly, what is the oxygen consumption when he is swimming at a speed of 1.5 meters per second? So I'd go over to 1.5 meters, and go here, it's about 10 liters per minute. So you could say, you could write 10, or you can remember these double squiggly means about 10. Was it liters per minute? Yeah, liters per minute. Okay. Question 3 asks, what is the oxygen consumption after 50 seconds of swimming? Well, if you notice here, oxygen consumption's here, but speed tells us our oxygen consumption. We're given 50 seconds. So I'm going to start on the left. I'll go to 50 seconds. That leads me to 2.5 meters per second, which is over here, which leads me to, let's go green, 25 liters per minute. which is our final answer. Because that's what we're looking for, oxygen consumption. Okay? So this one, we're going forward. We're starting with time and ending with oxygen. All right, now we're going to start with oxygen and try to end with time. So I'm going 15 liters per minute. Gives me, let's look, 15 liters per minute gives me 2 meters per second, which leads me to 30 seconds. Well, notice the connector here is speed. Connection is speed. All right. Let's keep going. These are so fun. Aren't they fun? Yeah, they're so fun. They're sick. All right, here we go. So, again, let's do another question about this. What does the function represent, g of f of x represent in real life context for a swimmer? All right. So, where am I starting? Let's start from the inside out. When I input x, this x right here is time. Okay. When I apply f, when I apply my function, if I apply time, my output is speed. I go from speed as an input, and my output becomes oxygen. Oxygen use. Okay? So what does this thing represent? Well, if I jump from here to there, my first circle back to the beginning leads to my second circle, which leads to my third. Okay? Like that. You could think about it as oxygen use and how it relates to time, or oxygen use based on time. Okay. Real world. Wow. All right. So what I want you to do, you're going to pause the video in a second. You're going to do this one here, and then you're going to try this one there. And then we'll kind of talk about this one at the end a little bit. But I want you to try here, h of g of x, then h of f of g of x. All right. So pause that thing. Pause it. Pause it. Pause. All right. Here we go. So let's go h of g of x first. So h of g of x, I substitute g in for x in h. Okay, and you could leave it like this: 3 times the quantity, the square root of 9x minus 4 all cubed plus 5. Or you can recognize and rewrite that as a fractional exponent. Realize that the square root gives you a 2 in the denominator. The square root of x to the 1/2. Okay, plus 5. Either or are acceptable. All right. So I'm going to show you, we're going to do h of f of g of x. So I'm going to show you a little more, something that's similar to this, a little more complicated, then I'll break it down for you a little bit. Okay. So this might be confusing. H of f of g of x. So I have g plugged in to f, plugged in to h. Okay. Let's break that down because that's a lot. So I start from the inside and work my way out. F of g of x. F of g of x, that means I'm going to take g, substitute it in for x in f. Alright, so and gives me the square root, okay, of 9x minus 4, quantity squared. Well, square root and the squared cancel out. I'm left over with 9x minus 4. So now I'm going to take this 9x minus 4 and substitute it in for x into h. Okay, so that's h of 9x minus 4, which is 3, quantity 9x minus 4 cubed, plus 5. I like this way a little bit better, alright, just going step by step. It helps me to visualize it and see it, okay? Either way is fine. But either way, you should realize that these two cancel out, and this should be your final answer. G of h of 2, I went ahead and did. Okay, inside out, h of 2 gives me 3 times. You plug in 2 for x, you should get 29. Plug 29 into g, and you get square root of 257. And that's it for the composition of functions. We have one more video for Unit 2. It's exciting stuff. Adios.